Hello and welcome to Math 270 Linear Algebra here at Cañada College. My name is Lapuz and I'm the instructor for the course. This is a video series that discusses the concepts in each section, and this is our very first one, Chapter 1, Section 1.1. This chapter is called Systems of Linear Equations. And in our first section, we will introduce ourselves to systems of linear equations. We will try to recognize what a linear equation is and find parametric representations for the solution sets. We will determine whether a system of linear equations is consistent or inconsistent. And we will use back substitution and Gaussian elimination to solve for these linear equations. First, let's take a look at the idea of what is a linear equation in n variables. By definition, a linear equation has n variables, and for the sake of not having to find enough alphabets or letters in our alphabet, we will just use subscript. So x sub 1, x sub 2, x sub 3, all the way to x sub n are going to be our n variables. And a linear equation is an equation of the form where we have a constant times the first variable plus a constant times the second variable, etc. These constants that are being multiplied with the variables are called coefficients. And the term on the right hand side of this equation, our b term, is called a constant term because it's not being multiplied by any of the variables. And the first number, a sub 1, is called the leading coefficient, and x sub 1, our very first variable, is called the leading variable. So we can think about x sub 1, x sub 2, x sub 3 as like x, y, z. But then if we want to go higher dimensions than that, then we're out of letters, and so that's why we use these subscripts. So once we know the definition, we should identify when things are linear equations and things are nonlinear equations. The first three examples here are linear equations. You can see that 3x plus 2y is equal to 7 is a linear equation in x and y. Our second one, 1/2 x plus y minus pi times z is equal to square root of 2, is also a linear equation. That's a linear equation in x, y, and z. Those are your variables. Our constant term is square root of 2, which is just a number. And our coefficients are 1/2 for x, 1 for y, and negative pi as a coefficient for z. Our third example here, sine pi, is just the constant. It's a number, and that is being multiplied by x1, so that's our leading coefficient, and our leading variable is x1. Our next coefficient is negative 4 being multiplied with x2, and our constant term is e squared. I think more importantly in identifying linear equations is to be able to identify a nonlinear equation and explain why that is nonlinear. So each of these next three equations are nonlinear. The first one, x times y plus z is equal to 2, is nonlinear because the two coefficients, or the two variables, x and y, are being multiplied by each other. They do not work as coefficients of each other. Instead, they are variables, and since you're multiplying them, then it doesn't work anymore. So that's nonlinear. B is nonlinear because the variable x is being raised as a power of e. It's not being multiplied by a constant. Instead, it's being put into the function, the exponential function e to the x. So that is nonlinear. Similarly for c, the leading variable x1 is actually being put into a sine function. It's not being multiplied by sine. It's the sine of x1, and that makes it no longer linear. So it's important to identify when things are linear or not linear. And just so you know, for this class called Linear Algebra, we will only deal with linear equations. Next, let's take a look at solutions and solution sets. So by definition, a solution to a linear equation of n variables is a set of numbers. We'll call it s sub 1, s sub 2, all the way up to s sub n. So that if you put s sub 1 in for x sub 1, and you put s sub 2 in for if you put s sub 2 in for x sub 2, then all your equations would work. So essentially s sub 1, s sub 2, s sub 3, all the way to s sub n are going to be actual constants, numbers, or values that we would get as a replacement for x sub 1, x sub 2, all the way to x sub n, so that all the equations would be true. It turns out that the set of all solutions is called a solution set, and you could just have one solution, you could have more than one solution, or you might not have any solution. So we'll take a look at those scenarios later on. Describe the entire solution set. We sometimes need to use parametric representation, and the parametric representation just means if we have more than one solution, then we might need to set a parameter to describe all the solution sets. Let's take a look at this example. We have a linear equation 3x plus 2y minus z is equal to 3. So that's only one equation we're dealing with, and the question is, what values can we put in for x and y and z so that we get this to be a true statement? It turns out that there's a lot of possible answers. We can set x equals 0, y is equal to 0, and z equal to -3, and that would work. We can set y equals 0 and z is equal to 0 and x equal to +1, and that would work. And so we want to be able to describe all those solutions mathematically, and for that we will do what the solution tells us to do. We're going to choose x, y, or y and z to be free variables and solve for x. So if we solve for x, we're going to get x is equal to 1 minus 2/3 y plus 1/3 z. Now what we're going to do with that is we're going to let y, one of the free variables, equal to one parameter, we'll call s, and we're going to let z equal to another free variable equal to another parameter, we'll call it t. And so your solution set then would be x is equal to 1 minus 2/3 s plus 1/3 t, where y is equal to s and z is equal to t. So that way you can put in actual values for your free variable, like say we'll let s equal to 0 and t is equal to 0. We talked about this by letting letting y and z equal to 0, and then you're going to get an x variable of 1. And the same thing if you let y equal to 1 and z is equal to 2. If put that into the solved equation for x is going to be equal to 1. So you're going to get a whole bunch of these solutions, a family of solutions, and we'll talk more about the idea of how to describe these solutions geometrically. But in this case, we are able to find the solution using parameters. Finally, let's actually talk about a system of linear equations. And a system of linear equation is a set of linear equations. And notice now that since we're running out of subscripts, a1, a2, a3, and then we have another set of a1, a2, and a3. So instead of just calling it with one subscript, we're going to call it a sub 1, 1 having two subscripts. So we have a sub 1, 1 times x sub 1, a sub 1, 2 times x sub 2, etc. And then the next row we have a sub 2, 1, x1 plus a sub 2, 2, x2, etc. And so that way we can describe this as general as we need to. All right, so a system of linear equations called the linear system. and the solution would be not all a set of S1s and S2s such that it satisfies the equation when we put it in for X1, X2, etc. Here are some examples of systems in two variables. So instead of X1 and X2, we'll use X and Y since that's a little bit more convenient, and they want us to solve for this. So I'm hoping that you've seen these problems before in your algebra class, way back in your algebra class. And these are just our first simple set of examples of systems of linear equations in two variables. Our first example, we can think about x plus y is equal to 3 and x minus y is equal to -1. We can graph that and we can see that the place where they intersect would be the solution for this system. So when x is equal to 1 and y is equal to 2, they satisfy both equations, and graphically you can see that that's where they intersect. How to solve for that? Well, you can use either the substitution method or the addition method as what you might have learned in your algebra class. Our second example looks like there could be infinitely many solutions, and so for this particular scenario, if we have an infinitely many solutions, we would want to introduce a parameter and have a parametric representation for the solution set. In this case, we actually will see that the two lines that we're looking at, x plus y is equal to 3 and 2x plus 2y is equal to 6, is exactly the same line. And so to represent this, we would just let y equal to t, and then solve for y, or solve for x, so that x is equal to 3 minus t, and then any of those, by letting t equal to any value, you can find your x value, and then you can have that ordered pair or the solution set. So in this case, we have infinite number of solutions, and our two lines actually coincide and are exactly the same. And then our last example, we have x plus y is equal to 3 and x plus y is equal to 1. Turns out to be two parallel lines. So graphically, being that they're parallel, they do not intersect, and so they will have no solutions. So in this particular scenario, we have a case where our system has no solutions. And so if you try to put any value for x and y, you can never have both of these equations to be equal to 3 or 1 at the same time. All right, so to summarize the set of scenarios that we have, if we have a system of linear equations, this, our example was just for two variables, but this can happen for as many variables as you want. But if you have a system of linear equations, you either one, have exactly one solution, or two, if you have more than one solution, then it's going to jump to an infinite number of solutions. In other words, you can't have just exactly two solutions for your system of linear equations. So if you have more than one, we're going to be at the infinitely many solutions scenario. Or the third case, you have no solutions at all. So those are your three possible scenarios for systems of linear equations. Here's another example where we have three variables and three equations, and our variables are x, y, and z. How can we solve for this system? Well, we can do some fancy substituting, solving for one variable and one equation and putting it into the other equations, etc. But here we're going to start learning a particular algorithm for solving for these things. We're going to work, it says here, to work with the upper left corner, saving the x on top. And what we can do is we can add the first equation to the second equation and then replace that that second equation. Or rather, we're going to adding the first equation to the second equation produces a new second equation. And so that is going back to the example. If we add x plus negative y, we're going to get 0. If we add negative 2 plus 3, we're going to get positive y, or negative 2y plus 3y, we're going to get positive y. And then we add 3z plus, there's nothing here, so that's just going to be 3z. And then we add 9 plus negative 4, that's 5. So we're going to get positive y plus 3z is equal to 5. So that is our first equation. And then now we're going to add adding negative 2 times the first equation to the third equation, and then we're going to come up with a new third equation. So we'll multiply the first equation by looking at the first set. First equation by negative 2, add that to 2x, we're going to get 0. And negative 2 in the first equation will give us positive 4. Positive 4 minus 5y, or positive 4y minus 5y will give us a negative y, etc. So you'll get these other two values. So now we have this new set of systems, or a new system, new set of equations. And then we can do the same thing. We can, let's say, add the second equation to the third equation, and we're going to be able to eliminate the y variable that way. And if we do that, our last equation will end up looking like 2z is equal to 4. And then from there you can solve for z. We can divide out by 2, and we're going to get z is equal to 2. And then now that we know that z is equal to 2, we can put it back into the second equation. We get y plus 3 times z is equal to 2, so y plus 6 is equal to 5, and we can solve for y and get negative 1, and then we'll put those values in to solve for x in the first equation. So that's called back substitution. We solve from the last variable z, and then we substitute it back to solve for the next to the last variable y, and then we substitute those values back to solve for the first variable x. So in this case, we're able to find the solution. Now, we did this using equations and combining equations and things like that, but we'll see in the next chapter that it would be a lot better to put this in matrix form so that, you know, we don't have to keep track of the x and y's and z's, all those variables. We can just see it in a nice compact set of or enclosed matrix of constants. Graphically, if you were to pick up a three-dimensional grapher or find a three-dimensional grapher in the internet, if you put those three equations back into that graphing program, you'll see that they're just a bunch of planes. Well, there are going to be 3 planes, and those 3 planes happen to intersect in a point, and the point that we're looking at here is 1, negative 1, 2, and that is the one point of intersection. Okay, so that is our first section. And I hope that you can take a look at this presentation, take a look at the PowerPoint that's going to be available for you as well, and walk through the presentation. We'll do a few more examples to get us going, but hopefully this is enough information for you. A lot of this is introduction, some terminology in the beginning, but you know, some examples that you might have hopefully have seen before in your algebra classes. Okay, all right. Have fun. Good luck.